Good day everyone and welcome to our presentation.
I'm excited to introduce the work of William Peebles and Sainin C., titled Scalable Diffusion Models with Transformers. This groundbreaking research challenges the conventional use of UNet architectures and diffusion models, proposing a transformative approach with diffusion transformers or DiTs. Stay tuned as we delve into how this shift can enhance scalability and performance in generative modeling. Let's begin. In this slide, we delve into the key highlights of our research. We've introduced a new class of diffusion models which we call Diffusion Transformers or DiTs. These models are based on transformers and have shown to outperform traditional UNet models in terms of scalability and efficiency. Now let's talk about the relevance of UNet inductive bias. Our research shows that the UNet inductive bias is not crucial to the performance of diffusion models. In fact, diffusion models can greatly benefit from adopting standard designs like transformers. This opens up new possibilities for cross-domain research and allows diffusion models to inherit best practices and training recipes from other domains. In essence, our work demystifies the significance of architectural choices in diffusion models and provides empirical baselines for future generative modeling research.
Stay tuned as we delve deeper into the specifics of DiTs and their potential applications.
In this slide, we delve into the key highlights of our research. We've constructed and benchmarked a design space for diffusion transformers or DiTs under the framework of latent diffusion models, also known as LDMs. Our findings reveal a strong correlation between the complexity of the network, which we measure in Gflops, and the quality of the sample, which we measure using the Fréchet inception distance or phi-d. This correlation is significant as it allows us to predict the performance of our models based on their complexity. This understanding of the relationship between complexity and quality is a crucial step in the development and optimization of diffusion models. In the next slides, we will delve deeper into the specifics of our DiT models and their performance.
In this slide, we're taking a closer look at the architectural choices in diffusion models. We're challenging the prevailing notion that UNet inductive bias is essential for these models.
As you can see in the figure, we've used diffusion transformers or DiTs for ImageNet generation. The graph shows the performance of DiTs in terms of FID50K at 400K training iterations. Notice the improvement in phi-d as model flops increase. The best model, DiT-XL2, outperforms all prior UNet-based diffusion models. This suggests that there's potential for improved performance and scalability in generative modeling research by exploring different architectural choices. In our quest to improve the efficiency of diffusion models, we've turned our attention to the prevailing solution, the convolutional UNet architecture.
While it has seen success, we believe there's room for improvement. The UNet design is primarily comprised of ResNet blocks, which while effective may not be the most efficient choice.
Now let's take a look at this figure. It showcases the performance of our proposed solution, the diffusion transformers or DiTs.
As you can see, as the model complexity increases, so does the performance in terms of FID50K at 400K training iterations.
Most notably, our best model, DiT-XL2, outperforms all prior UNet-based diffusion models. This is a promising indication that our approach could lead to more efficient and effective diffusion models. In our quest to improve diffusion models, we've proposed a new solution, diffusion transformers or DiTs for short. These are a new class of diffusion models that are based on transformers. They adhere to the best practices of vision transformers or ViTs, which have been shown to scale more effectively for visual recognition than traditional convolutional networks. Now let's take a look at this figure. It shows the performance of DiTs in terms of FID50K at 400K training iterations.
As you can see, there's a clear improvement in phi-d as model flops increase.
Most notably, the best model, DiT-XL, outperforms all prior UNet-based diffusion models. This is a significant leap forward in our field and opens up exciting possibilities for future research. Let's delve into the scaling behavior of transformers. We've conducted a comprehensive study examining the relationship between network complexity and sample quality. This is illustrated in the figure, which shows the performance of diffusion transformers, or DiTs, in terms of FID 50K at 400K training iterations. As you can see, as model flops increase, there's a significant improvement in FID.
In fact, our best model, DiT-XL/2, outperforms all prior UNet-based diffusion models.
We've also constructed and benchmarked the DiT design space under the latent diffusion models framework. This has allowed us to successfully replace the UNet backbone with a transformer, demonstrating that DiTs are scalable architectures for diffusion models.
This is a significant step forward in our research, and we're excited to share these findings with you today. In this slide, we delve deeper into the scalability and performance of diffusion transformers, or DiTs.
As you can see from the figure, there's a strong correlation between network complexity, measured in Gflops, and sample quality measured by FID. This correlation is a testament to the scalability of DiTs. Moreover, by scaling up DiT and training an LDM with a high-capacity backbone, we achieved a state-of-the-art result of 2.27 FID on the class-conditional 256 x 256 ImageNet generation benchmark. This outperforms all prior UNet-based diffusion models as shown in the figure. The figure illustrates ImageNet generation with DiTs, showing the improvement in FID as model flops increase. The best model, DiT-XL, stands out, demonstrating the potential of DiTs in this domain. In summary, the scalability and performance of DiTs make them a promising tool for future research and applications. In our exploration of related works, we first acknowledge the transformative role of transformers across various domains.
These models have replaced domain-specific architectures in language, vision, reinforcement learning, and meta-learning.
They've shown remarkable scaling properties and have been trained to predict pixels auto-regressively and on discrete codebooks. Next, we delve into the success of diffusion models and image-level generative models.
These models have outperformed generative adversarial networks in many cases, with improvements driven by enhanced sampling techniques.
However, for these diffusion models, convolutional UNets have been the default choice of backbone architecture. In this study, we challenge this norm and explore the use of pure transformers, introducing a new class of diffusion models based on transformers, which we call diffusion transformers, or DiTs.
We'll discuss more about this in the following slides. Moving on to related works, we see the transformative impact of transformers.
These models have replaced domain-specific architectures across various fields, including language, vision, reinforcement learning, and meta-learning. Their remarkable scaling properties under increasing model size, training, compute, and data have been widely recognized. Transformers have found significant use in autoregressive models and vision transformers, or VITs. Furthermore, they have been applied in denoising diffusion probabilistic models, or DDPMs, to synthesize non-spatial data. This broad application and adaptability of transformers underscore their potential in advancing generative modeling research.
In our exploration of related works, we delve into the realm of diffusion models and the UNet architecture.
The UNet architecture, introduced by Ho et al., has been a cornerstone in the field of diffusion models. It has seen significant success within pixel-level autoregressive models and conditional GANs. The UNet architecture is primarily composed of convolutional layers, with the inclusion of ResNet blocks, which are a key component of its design. Furthermore, it incorporates spatial self-attention blocks, particularly at lower resolutions, enhancing its performance. This exploration of related works sets the stage for our innovative approach, which we will discuss in the following slides. In our review of related works, we've identified some limitations in existing approaches. Firstly, the convolutional nature of UNet, which has been the backbone of diffusion models, may lead to efficiency and lack of scalability. Despite the potential for improvement, the high-level design of UNet has largely remained unchanged. Secondly, in the image generation literature, architecture complexity is often evaluated using parameter counts. However, this method has its limitations as it doesn't account for factors like image resolution, which significantly impacts performance. In our research, we've taken a different approach, focusing on the transformer class and introducing diffusion transformers or DiTs to address these limitations.
In our exploration of related works, we've seen the transformative impact of transformers across various domains.
They've been used in discrete codebooks as both autoregressive models and masked generative models, demonstrating excellent scaling behavior up to 20 billion parameters. On the other hand, diffusion and score-based generative models have made significant strides in the field of image generation, often adversarial networks or GANs. The advancements in denoising diffusion probabilistic models or DDPMs have been largely driven by improved sampling techniques. These findings set the stage for our research, where we delve deeper into the architectural choices in diffusion models and their impact on performance.
Stay tuned as we unravel our findings in the upcoming slides. On this slide, we delve deeper into our proposed research and its technical details. We present the Diffusion Transformers or DiTs, a novel class of diffusion models that are based on transformers.
As you can see in the figure, the DiT architecture is designed to be as faithful as possible to the standard transformer architecture. This is to retain its excellent scaling properties, which have been proven effective in vision transformers or VITs. VITs are known for their superior scaling capabilities in visual recognition tasks. By adhering to the best practices of VITs, DiTs are poised to bring about significant advancements in the field of diffusion models. On this slide, we delve into the technical details of our proposed research. As you can see in the figure, we present the architecture of the diffusion transformer, or DiT. We've identified some limitations with the current UNet architecture used in diffusion models. Its convolutional nature and reliance on ResNet blocks have posed some challenges.
This led us to explore alternatives, and we found that transformers could potentially offer a more efficient and scalable design. This is the problem we're addressing with our research.
We believe that by replacing the UNet backbone with a transformer, we can improve the performance and scalability of diffusion models.
On this slide, we delve deeper into the technical details of our proposed solution, the Diffusion Transformers or DiTs.
As you can see in the figure, the DiT architecture is designed to be as faithful as possible to the standard transformer architecture, retaining its excellent scaling properties. Our approach to the problem involves constructing and benchmarking the DiT design space under the latent diffusion models framework. This allows us to train diffusion models within a variational autoencoder's latent space, effectively replacing the traditional UNet backbone with a transformer. One of the key aspects of DiTs is their scalability. We found a strong correlation between network complexity, measured in giga floating point operations per second, and sample quality, measured by the fresh inception distance.
This suggests that as we increase the complexity of the network, we can expect a corresponding increase in the quality of the samples generated.
This scalability is a promising feature of DiTs, opening up new possibilities for future research and applications. Let's delve into the technical details of our research. As you can see in the figure, we present the architecture of the Diffusion Transformer, or DiT.
We've scaled up DiT and trained a latent diffusion model, or LDM, with a high-capacity backbone, achieving a computational complexity of 118.6 Gflops.
This approach has led us to a state-of-the-art result of 2.27 D on the class-conditional 256 x 256 ImageNet generation benchmark. When we compare the performance of DiTs with prior UNet models, we see that DiTs not only outperform them, but also exhibit superior scaling properties inherent to the transformer model class. This is a significant step forward in the field of diffusion models. Moving on to our key results, we've introduced a new class of diffusion models based on transformers, which we call Diffusion Transformers or DiTs. These models follow the best practices of vision transformers, known for their effective scaling and visual recognition. Our research shows that DiTs are scalable architectures for diffusion models, demonstrating a strong correlation between network complexity and sample quality. By scaling up DiT and training a latent diffusion model with a high-capacity backbone, we achieved a state-of-the-art result of 2.27 D on the class-conditional 256 x 256 ImageNet generation benchmark. As you can see in the figure, DiTs outperform prior UNet models and inherit the excellent scaling properties of the transformer model class. This implies that DiTs have great potential as a scalable and efficient architecture for diffusion models, outperforming traditional UNet models. In our study, we introduced a new class of diffusion models based on transformers, which we called Diffusion Transformers or DiTs. These models have shown to outperform the prior UNet models and exhibit excellent scaling properties, making them a promising avenue for future research. We also delved into the significance of UNet's inductive bias in diffusion models. Our findings suggest that the performance of diffusion models is not heavily reliant on UNet's inductive bias. This opens up the possibility for these models to benefit from architecture unification, specifically by adopting transformers. This could lead to improved scalability, robustness, and efficiency in diffusion models. In conclusion, our work has shed light on the potential of transformers in the realm of diffusion models, and we believe this could pave the way for exciting advancements in generative modeling research.
In conclusion, we've seen that diffusion transformers or DiTs are highly scalable architectures for diffusion models.
There's a strong correlation between the complexity of the network measured in Gflops and the quality of the samples measured by phi-d. This scalability has allowed us to achieve state-of-the-art results. We scaled up a DiT and trained a latent diffusion model with a high-capacity backbone, achieving a remarkable 2.27 phi-d on the class-conditional 256 x 256 ImageNet generation benchmark.
But we're not stopping here.
The promising results we've seen with DiTs suggest that future work should continue to scale these models to larger sizes and token counts. We also see potential for DiTs to be used as a backbone for text-to-image models, opening up new avenues for exploration. In addition to these achievements, we've also seen the impact of scaling on metrics beyond phi-d. As we increase the scale of DiTs, we see improvements across a range of valuation metrics, including inception score and precision.
We've also observed that increasing the scale of DiTs leads to a more rapid decrease in training loss, which saturates at a lower value. This is consistent with trends we've seen in language models where scaled-up transformers demonstrate improved performance on downstream evaluation suites. In our experiments, we've also found that applying guidance to a subset of elements can still yield good performance. This is an interesting phenomenon that we believe warrants further exploration in future work. Thank you for your attention, and we look forward to sharing more of our findings in the future.
In conclusion, our work with diffusion transformers, or DiTs, has shown promising results. We've seen that they outperform previous UNet models and have excellent scaling properties. Looking ahead, we plan to continue scaling DiTs to larger models and token counts.
We also see potential in exploring DiTs as a backbone for text-to-image models.
Our findings have opened up new possibilities for cross-domain research and provide empirical baselines for future generative modeling research.
In terms of implementation, we provided detailed information about our DiT models, including training loss curves and Gflop counts. We've also found that applying guidance to a subset of elements can yield good performance, a phenomenon we plan to explore further.
Finally, we've observed that scaling has a significant impact on various metrics, including phi-d, SFID, inception score, precision, and recall.
Increased model scale has shown to be beneficial, and we found that model Gflops are highly correlated with performance. Thank you for your attention, and we look forward to sharing more about our work with DiTs in the future.
In this slide, we delve into the conclusions and remarks of our study. We've discovered that the scaling behavior of transformers provides valuable insights for the design and optimization of future diffusion models. By examining the relationship between network complexity and sample quality, we've been able to identify key factors that influence the performance of these models. This understanding will be instrumental in guiding the development of more efficient and effective diffusion models in the future. As we continue to scale diffusion transformers or DiTs, we anticipate further improvements in model performance and efficiency.
This research opens up exciting avenues for future exploration and application in the field of image generation and beyond.